Thank you for the invitation to speak in the seminar. It's a great pleasure to be attending all the talks throughout the last few months and to give a talk here too. So everything I'm going to talk about today is joint work with Jackson Goodman. And I want to begin just recalling something that Thomas already discussed, this notion of rigidity and extremality for scalar curvature. So I want to somehow draw a finer line between the words extremal and rigid here, following what Gromov does in most of the surveys. So if we have a Riemannian manifold, we're going to assume always oriented with a metric G. We could try to build a competitor metric that has larger scalar curvature and larger areas. And so, for example, I was trying to find nice pictures to put in my talk, and I couldn't really draw better pictures. So I figured I would borrow from some nicer things that I could probably come up with. So if you take, let's see, I try to match the colors. For example, this little sphere here, you could try to compare it with that sphere there. It may be a little bit smaller, so it has higher scalar curvature, but the areas shrink, right? So you can't really achieve both of these inequalities for spheres, at least. That's how we learned from Thomas' talk, result of the rule. But there's sort of two ways in which this can fail. So first, this notion of extremality would be if whenever you have these inequalities, the scalar curvatures are actually equal to one another. So we could imagine that inequality forces equality of the functions, or there's a stronger version in which the metric tensors themselves coincide, right? So G and G prime are the same metric. And to keep things simple for most of the talk, I want to focus on this notion of competitor metrics. We're just really changing the metric tensor and looking at this situation. But as Thomas also pointed out, there's this kind of topological modification that can be considered. And all of the results I'm going to discuss allow for some of these topological modifications. If there's time towards the end, I'll discuss a little bit more the details on how. But for now, let's just use the simpler version. And as a motivation, let's try to see what happens in dimension 2, which is perhaps a very simple situation that could give us some idea of what to hope for in higher dimensions. So if you have a sphere, so really I'm phrasing it in a way that should mimic what will happen in dimension 4, but if you have a simply connected closed Riemannian manifold to really oriented to a sphere, if you have non-negative curvature, then the metric is extremal in the sense that we just discussed. And if you have positive curvature, it's rigid. Let me perhaps just entertain the quick argument here using Gauss-Bonnet to show this. So using Gauss-Bonnet, you know that if you integrate the sectional curvature, and in dimension 2, scalar curvature and sectional curvature, of course, here are the same. So if I integrate the sectional curvatures of the competitor metric and the original metric against the corresponding area elements, of course, I get the same quantity. So this difference here is 0. And because of the inequalities, since I have larger sectional curvature and area and than the original metric, this here is bigger than or equal to the integral of sectional curvature of the competitor metric when I replace the area element by the area element, let's say, which is a conformal factor of the original one. So using uniformization, I can just write out a conformal factor here. So e to the 2u would show up next to this curvature, and then I can subtract the original metric with this area element. But if the areas are larger, this conformal factor is bigger or equal than 1. So this here is bigger or equal than the integral of the sectional curvature of G prime minus the sectional curvature of G. Which we're assuming is non-negative, right? So if that integrates to 0, they have to be equal to one another. So you have extremality, right? So that's perhaps how one could argue here. And for rigidity, you can actually cancel out this conformal factor. So if you know that the sectional curvatures are equal, if we have equality here between these two quantities, and we know that they are positive, then I can go back to this stage, and I know this is also 0, so these two quantities are equal to one another. So I can have the conformal factor in here. And because these are positive quantities, I can just divide by that, and I end up getting that the conformal factor is 1. So the metrics are actually equal to one another, right? So, so we get rigidity. Okay, and perhaps one could hope that this sort of situation is more general, that non-negative sectional curvature perhaps could be enough to have extremality for scalar curvature in the way that we discussed. So that's sort of the background that I want to keep in mind for the results. So just as a quick reminder of also something that Thomas already was kind enough to discuss in a good amount of detail, the main results establishing rigidity and extremality, I guess, originate with LaRue, with contributions of Lawson, as we heard, for the round sphere. So here it's really just a round metric on the sphere in any dimension. And then building on work of Minou, Goethe-Semmelmann have these very nice results in which if you have non-negative curvature operator, so here RG for me is the curvature operator acting on wedge 2, then if this is a positive semi-definite operator, then the metric is extremal. And in addition, if you have that condition of the scalar curvature divided by 2 being bigger than Ricci, and Ricci being positive, then rigidity holds. They also have a result for Kähler manifolds. So here, non-negativity of the Ricci curvature is enough for extremality, and strictly positive Ricci curvature is enough for rigidity. But again, these are very special manifolds, right? So if you have non-negative curvature operator, these are symmetric spaces. So we're, the metric is extremely special. And here you have special holonomy, right? It's scalar. So other than on the sphere, where you could have positive semi-definite operator with a metric that you maybe flatten out a piece and it's not a symmetric metric, but other than a sphere, the only examples to which these results apply are either metrics of symmetric spaces or Kähler metrics, right, with special holonomy. So in light of that, I guess it would be very desirable, as Gromov says in this problem C in the survey, that it would be very desirable to have criteria for extremality and rigidity, and also describe particular cases of these metrics. And in low dimensions, perhaps there's some better hope of achieving this. So in dimension 2, we discussed it. Dimension 3 is a bit of a particular situation because most of the methods we're going to use are Dirac methods, and LaRue's result holds there, but it's really the round metric. But in dimension 4, there is a lot that one can exploit to say something about extremality and rigidity and build criteria. So that's kind of the main point of my talk. So what happens in dimension 4? And the key ingredient to analyze dimension 4 is this result that I'm stating here as Finsler Thorpe's trick. This in the geometric analysis community became known as Thorpe's trick. It's something that arises in Thorpe's work in the 70s, but really it's an instance of something that goes back a lot earlier. As I guess we heard today a few times, some of these results sometimes show up many years before what people realize at some point. So Finsler in 36 actually observed something for quadratic forms that implies this. So the statement is that sectional curvature is very tightly related to the curvature operator. So in dimension 4, the curvature operator lives in the same space as the Hodge star. So here, star is the Hodge star operator acting on 2 forms or bivectors, right? And non-negative sectional curvature is equivalent to the existence of some function that I'm calling tau, such that if I modify the curvature operator by adding to it tau times Hodge star, that modification is positive semi-definite. Okay, so this is precisely the direction in which symmetric endomorphisms of the space fail to satisfy the Bianchi identity. So in some sense, this is giving up the first Bianchi identity. And there's also strict versions of this. So if you want strictly positive sectional curvature, this is equivalent to this being true with a strictly positive definite modification of the curvature operator. You can flip the sign. This is a very general fact. So using this and using this to build on the work of Goethe-Semmelmann and Leroux, here's what we can prove. So this is, again, joint work with Jackson Goodman. So if you have a simply connected four manifold, and you assume it has non-negative sectional curvature, so you know such a tau exists, and then we want to make an assumption on this tau. I'd like to assume that the function tau can be chosen either non-positive or non-negative, so in a way that doesn't change sign, then the metric is extremal. And if in addition you have the condition from Goethe-Semmelmann on scalar curvature over 2 being bigger than Ricci, and Ricci being positive, then rigidity holds. Okay. Before anything else, let me point out how this applies to give new examples. So CP2 connected some CP2, it admits non-negative sectional curvature, for example, metrics built by Cheeger. And the function tau that you have there actually can be chosen to have a sign. So as a consequence, it has extremal metrics. It has extremal metrics with non-negative sectional curvature, and these are Cheeger metrics. And also, even back to CP2, which was known, for example, the Fubini-Studi metric or nearby Kähler metrics were known to be rigid by Goethe-Semmelmann. You can actually prove that there's a whole neighborhood of it in the space of Riemannian metrics, which is formed by rigid metrics. So here I can actually upgrade this to rigidity. Sorry, I can actually say rigid. And in the notion that, in the way that I discussed in the first slide. And CP2 has an open set, of rigid metrics. In particular, you get metrics with generic holonomy, right? So in both of these cases, you get generic holonomy, which is new, as we discussed. In particular, for CP2 connected some CP2, it's new in a more dramatic way because this does not admit any metrics with positive semi-definite curvature operator. It's not a symmetric space. And topologically, by Hodge theory, it does not admit Kähler metrics. So really no methods available before would yield rigidity on CP2. And this is, these two examples somehow fit nicely with what's currently known for non-negative curvature. So just to quickly point out, currently, and conjecturally, this is a complete list, but currently known examples of four manifolds, simply connected four manifolds with non-negative sectional curvature are just a sphere, projective space, product of spheres, and CP2 connected sum plus or minus CP2. So the sphere, again, has rigid metrics from Leroux. CP2 has the Fubini-Studi metric. S2 cross S2 has the product of spheres has non-negative curvature operator, so again has rigid metrics. CP2 connected some CP2 bar is a Kähler manifold, has Kähler metrics with positive Ricci, so again by Goethe-Semmelmann has rigid metrics. And now we can add CP2 to it. So then it follows that just like in dimension 2, all of the known examples have rigid metrics. So all of these all have rigid metrics. And those that have positive sectional curvature, again, currently, the only currently ones known to, but conjecturally the complete list, they have an open set of rigid metrics, right? So have an open set of rigid metrics. So let me maybe discuss a little bit why these two examples follow from the theorem. So let me maybe begin with CP2. So CP2, if you put the Fubini-Study metric, it's not hard to see that the curvature operator in a nice basis, you can diagonalize it, and you have eigenvalues 0, 0, 6, and then 2, 2, 2. So this is the self-dual part and the anti-self-dual part. I'm just mentioning that because Hodge star becomes very easy, right? These are eigenspaces for Hodge star. This is the +1 eigenspace and the -1 eigenspace for Hodge star. So it's clear that if you take R plus any number between 0 and 2, in particular, take constant equal to 1, so 1 times Hodge star, this is a positive operator, right? And then, of course, in a neighborhood of it, everything depends continuously on the metric. So in a neighborhood of the Fubini-Study metric, you can have a function tau, which does not change sign, okay? And you still have, you retain this property. So that is the case for CP2. CP2 connected sum CP2 works like this. You take this construction of Chigger, which is a doubling construction. So you take CP2 and you remove a ball. So then you have topologically, it's the normal bundle over CP1. So let's imagine you have CP1 inside CP2, and the normal bundle is this non-trivial disk bundle, right? This tautological bundle over CP1. The boundary of that is a 3-sphere. And you take 2 copies of it. So let's imagine I have another CP1 on this side, another disk bundle around here. Their common boundary is a 3-sphere, and you can deform the metric in such a way that near that boundary, the metric is a product. And then a product where we have really a cylinder with the round metric on the 3-sphere as the boundary. And so you can choose if you glue them with an orientation preserving or reversing isometry. You can use like a reflection or the identity or the antipodal map, whatever you want. So if you glue with a orientation reversing isometry, so here glue with an orientation reversing isometry, then you get CP2 connected to some CP2. If you glue with an orientation preserving one, of course, you get CP2 connected to some CP2 bar. Okay, and the metric, again, kind of goes up and becomes constant near the interface. But this area in which it's a cylinder, this area where it's a product, you can choose it to be arbitrarily small. So this kind of cylinder region can be infinitesimally thin, could be 0 volume, for example. And the function tau that achieves R plus tau Hodge star bigger or equal than 0, we can plot it here kind of like this. So tau, it's going to be 0 in this kind of central region where the metric is a product. But then outside that, it's going to be negative. So in one of these bundles, it's negative and arrives at 0. And when you glue to the other side, it just reflects this. It just goes down here the other side as well. So maybe this is the other side. Okay, so it doesn't change sign. Okay, you can write this explicitly with, for example, using using S coordinates. You can write this quite explicitly. The interesting thing, also, perhaps I should mention, is that these are really the only examples where the theorem applies. So in an earlier work with Ricardo Mendes, we found that this kind of property that the function tau does not change sign, it actually has some strong consequences topologically. So if you have a 4-manifold, again, closed simply connected 4-manifold with non-negative sectional curvature, and tau satisfying that can be chosen in a way that it doesn't change sign, then either the manifold is definite, and meaning it has definite intersection form. So then by Donaldson and Friedman, the manifold is homeomorphic to a connected sum of CP2s. Or if it is indefinite, then the situation is quite restrictive. Then it must be isometric to a product of spheres. So here's actually isometric to S2 cross S2 with a product metric. And so in that case, you already have Goethe-Semmelmann's result to give you rigidity. But the theorem would also apply. You also have a function tau here that doesn't change sign. So really, the theorem applies to all of these examples, with the only exception of CP2 connected to some CP2 bar. That's the indefinite manifold that would be missing here from this list. So that's why I painted it in gray. That's the only case in which the result does not yield rigid metrics. But then you can use the Kähler metrics as we discussed before. All right. So then I guess I can say something about a variation of this result, which Thomas also mentioned, that there's a version with boundary that was recently studied in works of John Lott and Cecchini Zeidler and others. So here, again, I'm borrowing from Kandinsky to try to draw you some kind of hemisphere. So imagine you have some kind of spherical hemisphere here. And of course, mean curvature, everything is going to be with respect to this unit normal that points inside for me. Okay, so, and then you can ask, okay, if I have a hemisphere here and maybe another hemisphere there, this one, it looks like the boundary would be totally geodesic. Maybe you have like 0 mean curvature there. And so to avoid the sort of easy way to cheat around extremality, you also need to require an inequality between the mean curvatures, right? So you have a competitor metric is something that has larger scalar curvatures and larger areas, but also larger mean curvature on the boundary. And typically here, you would also want to say larger than or equal as tensors on the boundary. For some technical reasons that I'll mention when I discuss an outline of the proofs, we actually need a slightly stronger version of this. I actually need to require equality here. So for the purposes today, extremality and rigidity with boundary in the result I'm going to state is with equality here. Then extremality is, again, when you get equality between the two geometric, between the curvature inequalities. So scalar curvature and mean curvature of the boundary of the competitor are equal to scalar curvature and mean curvature of the boundary of the original metric. And rigidity is the case where the tensors themselves agree. Okay. So there's a direct analog of the result I just stated for the case with boundary, provided that we assume the boundary is convex. So here I need the second fundamental form of the boundary need to be a positive semi-definite. So if you take any small geodesic ball, for example, in your manifold would have that, then the direct analog of the result holds. Namely, if you have non-negative sectional curvature and the function tau can be chosen in a way that it doesn't change sign, so it's either non-positive or non-negative, then the metric is extremal. And in addition, if you have this condition that appeared in Goethe-Semmelmann, then it's rigid. Okay, so just like the closed case, there's a special example perhaps that I should highlight, which is half the Chigger construction. So in this picture that I had before, you could imagine instead of gluing them, just take 1/2 of it and stay with it, right? So this has boundary. The boundary is a 3-sphere. You can arrange for the boundary to be even totally geodesic if you want. But that's topologically, that's the CP2 minus a ball, or it's the normal bundle of CP1 inside CP2. And this has rigid metrics in this notion, has rigid metrics by the same picture that I described before, because the function tau there didn't change sign, right? So these are, again, the same Chigger metrics, where you just stop at the boundary, you don't glue it. And the relevance of this example is that, for instance, if you try to use John's result, John Lott's result requires non-negative curvature operator and convex boundary. But if you have a manifold with non-negative curvature operator and convex boundary like this, then the bundle would be trivial. So this is a non-trivial bundle. It cannot have such metrics. Okay, so again, you need some actual function tau there. You can't just choose tau to be identically 0 and get away with it. This function is needs to be there. Okay, and perhaps a more even more interesting corollary of it, and that's why I'm calling it the sort of local version, is that you get a local result for manifolds with positive sectional curvature at a point. So suppose you have a manifold X where there's some point around X that maybe has, like around here, there's some point with all sectional curvatures at that point are positive. Then sufficiently small convex neighborhoods of this point, if I take for example, a geodesic ball, but any kind of sufficiently small convex neighborhood here is extremal in the sense that we discussed above. So this is quite easy to see from the theorem. So if you take a little neighborhood here, well, maybe that's too big, something like this, we can call this M. This is the ambient X. We can choose M in such a way that it's small enough so that all the sectional curvatures in M are positive. And we have a function tau, right? So from this, we know that there's a function tau such that R plus tau Hodge star is positive definite. Tau here is a function in M. And because it's strictly positive definite, I have actually an open set of such functions tau. I can wiggle them a little bit if I need to. So in particular, I can arrange for it to be such that tau of P is not zero. And up to shrink in M, I can arrange for tau to not change sign, right? So I can shrink M so that tau restricted to M does not change sign. And then I can apply the theorem, right? And so the upshot is that if you have a point with...
Can you remind what kind of rigidity, what exactly you mean? Because it's not rigid in the naive sense. Yes, what is the condition? Because the or, decreasing area or changing dm. What exactly this or means? I'm confused.
Okay. So the notion of rigidity I'm using here is this slightly stronger version where changing the metric on the boundary, I mean violating this equality. So
you keep the boundary.
Sorry?
You don't change metric on the boundary.
No, I don't change the metric on the boundary. We need...
but you can increase area. Wait, but this just cannot be true. This is not true. Yeah, you have a tiny little ball in the sphere, and a complementary sphere is everywhere bigger with the same boundary. Right? You take tiny little ball.
But the mean curvatures are different then, right? The mean curvature is always with respect to the...
A boss must have a positive mean curvature.
And
okay.
Yes,
so you have conditional mean curvature also. Okay. So you have conditional mean curvature and the scalar curvature.
Yes.
Okay.
Yes. So
but then for this example, okay. But then follows probably directly by doubling from at least extremality follows from got the Zemerman by doubling for all dimensions. Right, for the spherical case, for example, it follows for all dimensions. But you have more general conditions. That's the point.
Yeah. So we're just assuming positive sectional curvature.
Okay. Okay. Understood now. This is the point. Yeah. Okay.
Thank you. Yeah. So I guess I wrote the upshot very informally here, saying that yes, you can't increase scalar curvature or the mean curvature of the boundary in these convex neighborhoods of points with positive sectional curvature unless you decrease areas or change the boundary. But okay. All right. So I guess I can now say a couple words about the proofs. So I want to do that in a more or less unified way. So I'll discuss the closed case mainly, and then I'll discuss the small adaptations needed for the case with boundary. And it's going to follow exactly the framework that Thomas outlined. So indeed, it's in some sense, it's one more level of generalization of these ideas of using a twisted Dirac operator. The main difference I'll point out already is that the bundle we use is slightly smaller. So we need just the positive, the tensor product of positive spinors on both metric and competitor metric. But all right, so to get started, I stated the result in a way that did not fix orientation. So now I want to choose the orientation. So I have a specific sign on tau. And this is always a bit confusing, but it's easy when you write, when you look at this, because if I change the orientation, the curvature stays the same, but Hodge star changes sign. So if you had a tau which was bigger or equal than 0, I just need to change the orientation first so that tau is less or equal than 0. You change the sign of Hodge star as well. And so let's convention that tau is less or equal than 0. Okay, then we can build spinor bundles from both metrics, original and competitor. And I want to take the twisted bundle with just positive spinors of the original metric. And we have the usual twisted Dirac operator here. And we can compute the index of D plus. So this operator there, using the same standard tricks here that the Dirac operator is conjugate to D plus D star when you use the product of spinors, the product tensors of spinor bundles is just exterior algebra, right? So this here is going to be a difference of dimensions, right? This here is the index of D plus D star. But because we're restricting to this bundle where you just take positive spinors on both, this is the index of D plus D star restricted on positive even forms, if you look at the complexification of the exterior algebra. And so this is the dimension of the kernel of D plus D star on positive even forms minus the dimension of the kernel of D plus D star on negative odd forms, which we can compute in terms of Betty numbers, right? So if you add everything up, this is 1 plus the self-dual part of the second Betty number, so B2 plus, minus the first Betty number, but I'm assuming that the manifold is simply connected, so there's nothing here. And so this is always positive. There's always 1 plus something non-negative, so there's always index. And therefore, there's always a section, right, in the kernel. So that's the first part. It's the index theoretic part that ensures the existence of this section. And then the second part is applying, I guess, as we recently heard, I should add the name Schrodinger here. So I guess I wrote Bachner, Lichtenowitz, Weizenbach, which are usually the names that fly around, but I guess I should add Schrodinger to the list. So here we want to square the Dirac operator and see what curvatures come out. So it looks slightly menacing here with a lot of terms, but we'll see how these can be simplified. So we have the scalar curvature of the competitor metric, the scalar curvature of the original metric, and then these other two terms where I should tell you what T and this other thing are. So T here is the isometry between the wedge 2 of the two competitors. So I'll write somewhat informally like this. You take wedge 2 G prime, wedge 2 G. This is the map that relates that, right? So there's an invertible linear map here. So you conjugate, conjugate. I mean, you multiply the curvature operator on left and right by T and its adjoint, take the trace of that. That's this term. And then this other last term is what I want to point out about it is that it's linear in R. So L, fancy L of R is linear in the curvature operator R. And if you feed something non-negative into it, then it is non-negative itself. So this is non-negative if R is non-negative. And that's how the Goethe-Semmelmann proof works pretty much. But you don't have to feed R itself to it. It's just an algebraic construction that you can, for example, add in here a multiple of Hodge star. And if you do, then, for example, if you just put Hodge star itself, this is not definite, but when you restrict to positive spinors, tensor positive spinors, then it has a sign. Then this is bigger or equal than 0. And that's the reason why we need to restrict to this bundle at the end of the story. So we're only looking at positive spinors, tensor positive spinors, because there Hodge star has a sign, or rather L of Hodge star has a sign. And so we can do this, this very easy trick where you just add and subtract tau times Hodge star. L is linear. So here, by assumption, R plus T Hodge star is positive semi-definite. So then this whole thing is positive semi-definite. I am assuming tau is non-positive, and then L of Hodge star is positive semi-definite. So this whole thing is positive, right? So then this has a sign if we look at positive spinors. And that's all we need to get rid of it, right? We can start throwing things out. The other thing I want to throw out is this term with T, and that's just because if you have non-negative sectional curvature and an inequality between the areas, then you can estimate this term by the scalar curvature of G itself. So this is somewhat similar to what Goethe and Lehman do. They look at the whole curvature operator, but indeed the terms that you need are sectional curvatures for this part. So it's so you end up being able to combine these two terms. And here, instead of a quarter of this, you get a quarter of a half of the scalar curvature. So you end up getting another eighth. So added everything together, you end up with this nice formula where you have the rough Laplacian plus 1/4 of the difference of the scalar curvatures minus the scalar curvature of the original metric. Okay, and that gives you extremality because now we just apply it to the section we had from the index theoretic part, integrated, this is 0, but by this inequality, this is bigger or equal than that, right? So, so the inequality that we have here forces equality of the scalar curvatures. And the rigidity follows in the same way as Goethe and Lehman. So I'm not going to discuss that part. Okay. So I guess I can say maybe a couple words about the case with boundary. So it's again the same strategy, the same two parts, an index theoretic part, and I guess I should also add Schrödinger here. So the first part is a bit interesting here because we need a Patodi-Singer index theorem, right? We need boundary conditions for computing this index, and if you and that's where we need this is where we need the equality of the metrics on the boundary. So this is where we need G and G prime to coincide because we need to compute this finer index. And you end up seeing that this can be written as 1/2 of the Euler characteristic of M plus signature plus some contributions from the boundary, the 0th Betti number and the 2nd Betti number of boundary. And it turns out that whenever you have convex boundary and non-negative sectional curvature, you can apply the Soule theorem. You can use the Soule theorem to show that this quantity is always positive. So here you can actually do a case-by-case thing. We're in dimension 4. So you look at the dimension of the Soule, it's 0, 1, 2, or 3. And then you can actually see that in all cases, you get strict inequality. So there's always index. You don't need to assume anything. And so we always have a section that we plug in. And this other part is very similar to what I just discussed before. Maybe I'll just point out that in this inequality, I'm also using convexity of the boundary to integrate by parts and have this inequality work in that way. But then when you integrate by parts, you get a contribution from the boundary, which gives you the rigidity for the mean curvature part, right? So you have equality of the scalar curvatures and equality of the mean curvatures. So that's how the proof goes for the boundary case. Okay, so in the last part of the talk, I wanted to go back to something I mentioned in the very beginning, that you can actually allow these topologically modified competitors, right? So maybe I'll say a couple things about it, and I have my last image of Kandinsky that I want to borrow. That maybe you want to compare the sphere with something that has some holes in it, right? So you can add some handles and some more complicated shape, and imagine does that buy you any more room to increase scalar curvature and increase areas without being the same metric? So I want to maybe for shorthand, I'll define this class of competitor metrics C. So C here is a class of competitors where the dimensions for me are always going to be the same. I need to work in dimension 4 if I want to use these tricks. So even though the manifolds themselves might be different, I want both to be 4-dimensional. And and the maps are smooth spin maps with non-zero degree, right? So the degree, they're always oriented. So the degree is different from zero. And then extremality is the situation in which these two inequalities force equality of the scalar curvatures. So precisely as the analog of what we had before. So this should be equal to the composition for all F in my class of competitors. And rigidity is when the map F itself ends up being an isometry. So the pullback of this metric is just the other metric for all F in the class of competitors. Okay. And similarly for the case with boundary. So for the case with boundary, we add conditions on the mean curvature of the boundary, and F has to be an oriented isometry of the boundaries. Okay, so I'll just add similarly for case with boundary. Then with this notion, here's the slightly more general version of the theorem. So you take a closed oriented manifold and you define this class of competitor maps. So M is the original manifold, N is another four-dimensional manifold, and you want this inequality here to be true. So this is precisely what you need for the index to be non-zero. When you compute that index, I was assuming M and N were equal to one another, and I was assuming F was degree 1, was the identity. So then this here was that quantity that was positive. That was the index. But in general, you could have perhaps something that requires this, right? So again, the statement is that if you have non-negative sectional curvature, which is equivalent to the existence of some tau such that that's true, and tau can be chosen, let's say, less or equal than 0, since we're orienting our manifold already, then the metric is extremal. And extremal for this class C, so say C extremal. And if you have the scalar curvature over 2 bigger than Ricci, bigger than 0 condition, then it's furthermore rigid. And so you get this interesting situation where if you want to allow self maps of any degree, you can choose N to be equal to M, say N equal to M simply connected, and let's say definite intersection form, because as I mentioned before, this assumption that tau doesn't change sign, other than the product of spheres, will force the manifold to be definite. The only indefinite manifold with this property is the product of spheres, isometric to the product of spheres. So might as well assume definite. Then the class of self-competitors you get can be written like this. You get 4 plus 1 over degree minus 1 times the second Betti number bigger than 0. So in particular, if you have the second Betti number less or equal than 4, then you get self-maps of any degree. So when I stated the results a few moments ago for CP2 and CP2 connected some CP2, other than just comparing metrics directly on these manifolds, you could allow self-maps of any degree, since they have Betti numbers 1 and 2, right? And of course, if the Betti number is larger than 4, then this still works for maps of degree 1. But then again, most likely there's no non-negative sectional curvature on these manifolds, even though that's an open question.
But your maps are always assumed to be smooth, right?
Yes, my maps are always smooth.
Hmm.
Yes. Yes. So there's also the version with boundary, I guess. So I'll mention what the class of competitors that we can allow here is. So the map is, again, smooth spin, and restricted to the boundary, we need it to be an oriented isometry, right? So this is part of the class of competitors that we allow. And the index that needs to be computed is positive whenever this inequality here holds. So you have, again, Euler characteristics, signature, Betti numbers of the boundary, and signature of the original metric. And the statement is the same. If you have convexity of the boundary and tau less or equal than 0, then G is extremal for these competitors. And if you have strict, this other condition, then you have rigidity. Okay. So as I mentioned, the sole theorem here plays a very nice role, because if you then are concerned about this condition, well, it goes away by the sole theorem. So you can always use that it's a disk bundle over the sole, and this condition will always be satisfied. So the class simplifies if you're looking at self-compactors. If you're looking at n equal to m, it simplifies to just any smooth spin maps that are oriented isometries on the boundary. Okay, so that's the notion, for example, in which the normal bundle of CP2 with a Chigger metric is extremal. It's extremal with allowing for this class of competitors. Okay, so I think I'll finish a little bit early. I'll end here. Thank you.